shall we get started? Okay, so I'm going to continue from where I left off last time and sort of finish the first lecture, and then where I'm going to tell you a bit more about how we model state and how we do parsers and formatters and so on. And then there's going to be kind of a transition. I'm going to start my second lecture for real, and that's going to be about how we model cryptographic security in F star. So there's this kind of discrete transition at the end of it. Okay, so just as a recap, where we were last time was the last thing I showed you was how we model heaps in F star. I showed you how we derive specifications and give a model for operations that work on references like dereference and assignment. Okay, I'm gonna. If you don't mind, if those of you in the back, if there's some seats open in the front, given that there's we have the projector resolution and this font size is on, we have issues with it. If you can't see too well, I'd encourage you to come up as close as you can. I'm going to zoom in a little bit at least. And then we looked at how you can also give a model to freeing references. And now I'm going to, so that's just a recap where we left off. And now what I'm going to try to show you is that, in a way, these operations that manipulate references are actually just an instance of a more general pattern of doing data access through lenses. And lenses, I expect lenses, some of you are less familiar with it than you are with monads, but they're also an increasingly common structure in functional programming languages. And you can see a lens as just a abstraction of a accessor and a mutator of some structure. So a lens between A and B is a pair of functions, a get, which given an A, you can project out a B, okay? And a put, which says, if I have a B and an old A, I can get a new A out of it. So it updates the old A with its B component in some sense. So some examples of this is that, think of it as, let's say A might be a pair, say nat cross bool, and B might be, say, the bool, okay? And from a nat cross bool, you can get a bool just by projecting the second element. And if you're given a bool and a nat cross bool, I can get a new nat cross bool by updating the second element. So I think it's, it should all be quite familiar to you if you see it in those terms. It's just a getter and a setter packaged together, okay? So that's a lens. There's some laws associated with lenses, and I'm going to gloss over them, but you can roughly think of it as, if you get what you put in some sense. That's the main law in some sense. Or if you put twice, the first put doesn't matter, these kinds of things. But select and update, the two functions that I showed you on heaps, also form a lens. So if I have a heap and a reference into that heap, I can project out the value of that reference. So the getter, in some sense, is a projector for the heap. And the putter is the update function. Okay? So select and update form a lens. And these mutable versions, the imperative operations, bang and assignment, well, they are also kind of lenses, but they actually do destructive updates, the assignment does. So how do we view a destructive update in terms of this, purely functional lenses? Well, the general recipe is that you take imperative computations and you index them by a structure that's purely functional, and that index structure describes how the imperative computation behaves. We did that once already with WPs. Now we're going to do it again with lenses. Okay? So we saw, so I'm going to define a new kind of computation type. That's a derived form that says I have an ST lens. It's a stateful lens. It's indexed by an invariant and a pure lens. And this pure lens is going to somehow fully specify the behavior of the stateful operations. And this, so a stateful lens contains two functions, a stateful get and a stateful put. And they sort of have this, the stateful get sort of has almost the same signature as our pure get. It's a function from A to B, but rather than being a pure function from A to B, it's a stateful function from A to B. And in order to call this function, you need the invariant. It doesn't mutate the state, but what you get back out is fully described by the pure lens's getter. This thing is a full spec of this stateful code, in some sense. So you don't need to reason about the stateful code anymore. You can just reason about the pure structure. And the put is similar. I have a B arrow, a new B, an old A, and getting out a new A at the end of it. It's imperative. It's going to do it in place. Again, I need the invariant to call it, but its behavior, the value it returns and the final state, is fully characterized by the putter in the pure lens. Okay? And it turns out that you can package dereference and assignment as instances of these two types. So these two guys are an instance of an ST lens. So rather than reasoning about bang and assignment directly, you can just do it through an interaction of through the indirection of a lens. Okay? So that was kind of my example 2 of taking a computation, indexing it by a functional structure that has some nice algebraic properties. And now here's a third example. Okay, so here I'm looking at manipulating binary formatted data. So if you remember what I was telling you yesterday was that you have in some of the code we build, like these networking protocols, you want to parse and format network messages, ideally doing as few copies as you can, because this is a performance bottleneck. You want to sort of read directly out of a network buffer if you can manage it. So we have we have this library called EverParse. That's a parser generator, parser and formatter generator for these kinds of network formats. And to give you a sense of what these network formats look like, so this is a snippet from the TLS 1.3 RFC. So these RFCs, they're a mixture of English text with snippets in it of this semi-formal notation that looks kind of like C structs in some sense that describe network formats. And that's a convention used in these RFCs across many RFCs. So here's what it looks like for the client hello message in TLS 1.3 is a struct that looks like this. It's got a protocol version. It's got variable length fields. So for instance, there's a variable number of extensions whose length is between 8 and 2 to the 16 minus 1. So its length fits in a U16 basically. And each of these have some sort of description. You can give a formal semantics to this. It's yeah.
Are the structs intended to convey a layout?
Yes, that's right.
That's not C standard anymore.
This is RFC. This is RFC standard. So at the level, they pick a notation that looks like C structs, but it actually is just describing wire format. So it's bit precise. Okay. So parsing this stuff precisely is actually really important. In fact, many bugs that show up are in real code are really just parsing bugs in disguise. So Heartbleed, in some sense, was a parsing bug. So getting this stuff right is really crucial. And so how are we going to write parsers for this kind of densely coded network formatted data efficiently? Well, again, we put our functional programming hats on. We know how to write parser combinators. A parser, and say something like parsec, would be a parser from some bytes to, the parser might fail, but if it succeeds, it returns a T, and it tells you how many bytes of the input it consumed, so that you can compose it. And a formatter, you can see a formatter as being the dual of a parser, so that a formatter can be indexed by a parser, and a formatter is a function from a T to some bytes, such that if you run the parser on the formatted bytes, you get back the thing you started with. So parsers and formatters are inverses. Okay? Any questions about that? Should I read that? I went through that a little quickly. Do you all see it? All good? So we have these parsers and formatters, but ultimately what we want to do is we don't want to kind of, given a network message, we don't want to parse it into some high-level value, because doing so would incur copies. What I would prefer to do is to just know that I have a network buffer. I know it contains a valid representation of some high-level message. And if I want to access some field of that high-level message, I can just do it by going into the network buffer at a suitable offset, rather than doing any copies. That's what I'm after. Okay? So the way I'm going to structure this is to say, rather than having a parser, I'm going to have a validator and an accessor. A validator is a function that's just going to, it's a Boolean valued function that when applied to my network buffer is going to tell me whether or not it contains a valid t. Once I know that it contains a valid t, an accessor is a function that says, okay, its precondition is that the buffer is valid, and then it tells me if I want to access, I don't know, if I look at this, if I want to access, say, this field, the nonce in a client hello, the accessor is just going to tell me, okay, go read in the network buffer at offset 4. Okay? And it's going to come with a proof that tells me at offset 4, I have a valid representation of the nonce. Okay? So how does that validator look? Its type, sorry, I'm going to have to make this a tiny bit smaller. Oh, maybe not all the way smaller. Oh, good. I think you can see that's all of it. Okay. So a validator is indexed by a parser, and it takes as an argument an array of bytes, array of uint 8. That's a mutable array. That's my representation of my network buffer. And it's got a position. That's the position into the network buffer from which I'm supposed to start validating. Okay, and I need it for spatial safety, so that I'm writing a C program in disguise by doing this. So I need to worry both about spatial safety and temporal safety. Spatial safety means I have no buffer overruns. I don't access the array outside its bounds. And temporal safety means that if I'm going to read from this array, I better know that the array is still live, right? So this is a spatial safety requirement, that the position is within bounds. And I have a precondition for calling this function, which is my temporal safety requirement. If I'm going to read this array, I better know that the heap contains it, meaning that it's live. Okay? And what this function is going to return is an offset, a 2. That's my offset into my network buffer. That has several properties. So first, a validator doesn't change the state. Okay? And then it says, if the result is not an error code, okay, then there exists some value v such that if I run my specification parser on the byte representation of the array starting at the position, what I get back is a high-level value of type t. And I consume some amount of bytes. That says this is the case when parsing succeeds. And otherwise I say if my result is an error code, then parsing definitely failed on this. Parsing would have definitely failed on this. Okay, so that's kind of that's the soundness and the completeness of a validator. Okay, and but it's fully specified by just the parser. Okay. Now, if I have validators for the types I intend to read, I can build a combinator library of validators, and the combinator library of validators mirrors a combinator library for parsers. Just because the parsers are an index of the validators, I can just build a combinator library for the validators that just has exactly the same form as the combinators that you'd expect just for their indexes. So, for instance, I can have a unit validator. I can sequence validators. And the specification of a sequenced validator is just the sequence of their indexes. And I can have, that's bind and sequence, they're both roughly the same. I can map a function over validators, and what I get is a validator that behaves like the map of the function over the parser. So every operation I do on a validator is just lifted into the way it behaves on its index. So now if I want to write a validator for my client hello message, it's easy. I just compose all the combinators. This is kind of like what you would write in Haskell. Except this stuff is going to show up as a C program with 0 copies. Okay? And by construction, just by the types here and the way the combinators are set up, this sequentially composed validator refines a pure parser just by construction. One way in which you should read this index, validator with that index, is that this is imperative code that is a refinement of this pure code, of the pure spec. And you just get that just by construction. So now I need data accessors. I know that something is valid, and I want to go and actually read some fields out of it. And these are now my data accessors. And data accessors, here we come back to this idea of a lens. So ultimately, structured data access is like a lens. I have some raw data that's a valid, I know it's a valid T. I'm trying to project a field from it. Well, projection is like doing a lens read, right? So that's what an accessor is going to tell me. If I have, now it's indexed by 2 parsers and a lens. So it's saying, I'm going to go through this in maybe not as much detail as I did the prior specs. You can squint at it later online if you like, or ask me questions about it. But the basic idea is that if I know that my input buffer contains a valid P1, that means it contains a representation of a T1, and I know I have a lens from T1 to T2, then what the accessor is going to return to me is an offset, where if I parse the entire buffer, I get a value. Then if I project using the lens the T2 field of that value, what I get is something that I would get if I ran the parser at that offset. Okay? So concretely, the implementation of this would just be pointer arithmetic. But pointer arithmetic can be given this nice structured spec. We don't necessarily need to be, pointer arithmetic has this kind of bad rep, right? Like, hey, if you try to, you might sort of, if you did it by hand, you would very likely get it wrong, right? In some sense, the point I'm trying to make is that verification and functional programming actually gives you some kind of superpowers. You can write programs that you wouldn't dream of writing otherwise, or you'd be really ill-advised to write otherwise. Right? If you try to just say, I'm going to read from a network buffer at offset 17, you're going to get this wrong. You're going to get hacked. Right? But with full specs like this, you can write these kinds of super optimized programs, and you know that the type system's got your back. Right? So one of the high-level messages also I want to make is that, we shouldn't take verification as this kind of bitter pill that you have to swallow to get your programs right. I think we can have verified programs and make sure that our verified programs actually exceed the performance of unverified programs. And you wouldn't be able to do this if you didn't have verification. I think we're at a point where we can strive for that, and I think it's a completely plausible reality where we can have verification and performance at the same time. So what happens is that after verification, it's just dependently type programming, everything just normalizes. With partial evaluation, what you get out from F-star's extractor is a C program that has no allocation. It's just checking offsets into the buffer. And this thing can go fast. So here's some performance numbers. The higher is better. And these are some benchmarks that we ran on parsing TLS messages, Bitcoin transactions, and PKCS1 is a certificate format. So this number in the middle is, the blue number is 141 megabytes per second. That's the C++ SDK for Bitcoin, parsing Bitcoin transactions. With Everparse, we can generate those parsers, and it can be, this is like 13 times faster. Okay? So, yeah. Okay. Okay, Okay, so high-level message, write low-level code if you must, but program it tastefully and in a proof assistant, not directly in C or assembly, okay? And if you do, to make this fly, you need to think carefully about how to structure your imperative code so that verification is pleasant. And I think that's where, you put your functional programming hats on and you find nice structures, the proofs can be almost automatic. Okay, it takes a lot of, sometimes you have to get lucky in some sense. Okay, parsing is one of those domains where there's a lot of work already. We know the structures that one ought to use in the functional programming community, and that helps us structure our low-level validators. But I think that's where a lot of the interesting work is, new domains, finding those domains in which you can structure imperative code neatly. And with proofs, partial evaluation and erasure, your programs in the end can be significantly faster than handwritten C. All right, and that was homework from last time. So that's kind of the end of this, the tail of my first lecture. So I'm going to switch to talking about crypto, but before I do, happy to have questions about this part. Sorry. Yep.
Do you have an intuition for what makes it so much faster?
Yeah, you mean the case of Bitcoin?
Sure.
So I think there's, I think technically the main reason I think is that we really focus on doing zero copies. The Bitcoin parsers are written using C++, STL, and so on, and it makes for maybe idiomatic C++ code, but it's not necessarily tuned to be the fastest code out there. And perhaps for the Bitcoin SDK, in a way, another way you should interpret what I'm saying, or these performance as numbers, is that no one should really want to parse that fast. Right? That's not the bottleneck of Bitcoin. The crypto is. But, yeah.
Did you have numbers, on how fast you're parsing? Just curious, the code here.
Yeah. We had numbers for the. We had some.
Was that for desktop or portables or?
No, that was evaluated on a desktop. I'm trying to find it again. Sorry. There. So we're parsing at 1.8 gigs per second. Yeah. 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 Sorry, I don't. Okay, so switching a bit. Actually, you know what? If you don't mind humoring me for a second, I was really happy yesterday when I asked you guys here how many of you programmed and typed functional programming languages, and nearly all hands went up. And I want to do that again, and this time I want to take a picture. All right. So, how many of you program and typed higher order functional programming languages?
Oh,
yeah. Sweet. Thank you. What's that?
How are you going to prove you didn't ask for some
Oh, yeah.
You could
good
have
question.
asked, how many of you think it's a great idea to handwrite a parser in C?
Yeah. I think that's another message to take from this. If you're writing, as say, we've all written compilers and so on, right? And when you're writing a compiler, we're all completely used to using parser generators. And but in this area of people doing performance-sensitive, low-level parsing and formatting, like network messages and so on, they still resort to writing parsers by hand. And that's, I don't think it should be that way. And they do it because of performance. And I think whatever Parse is a parser generator for these low-level network formats where you get, you shouldn't, it's like YAC for network formats. Yeah. Yes? Yeah, I think it's actually, most of the proofs in EverParse, we spend a lot of effort in structuring proofs in EverParse so that the proofs happen largely by F-star normalization and some tactics, and we leave surprisingly few of the proofs to SMT in this case. I mean, I can speculate about why we ended up getting such good performance. One, I think it's just that we're trying to build this library that we can deploy, and so we're competing with a pretty high bar. Like OpenSSL is pretty fast already, and so we're trying to do everything in as performant a way as we can. So we're placing a high bar on ourselves to really push for that. The other is maybe we have this tool that lets you write and prove high-level code and get C code out of it that does not involve a GCE or anything. There are other systems that are sort of like this. Like, for instance, I can think of ATS. But I'm blanking now. Maybe someone here can think of another system that sort of works like this. But there aren't that many. So, yeah, I'm not sure that answers your question. It's speculation. Okay, so switching gears now. It's kind of quite a different talk. Modeling and proving cryptographic security. So I'm going to start with some sort of basic security background. So what we're looking at here is that we're in a setting where we're talking about communicating computational entities over a network, have a sender S and a receiver R. Okay, I'm going to make this bigger again. And they're communicating over a network, and there's an adversary sitting on the network that's polynomially bounded in some public parameters. And the adversary can tamper with messages that are going back and forth, both intercept and tamper with those messages. So that's the setting. And we want to make security claims about this kind of setting. There's two kinds of security claims that we're interested in, at least two. One of them is authenticity. So authenticity means that when the receiver accepts a message M from the sender, then the sender actually sent that message. Okay? So one way in which traditionally these kinds of properties have been formalized are by this idea of, missing a typo there, correspondence assertions on traces. So one way you can think of this is that you model a system as a trace of events. In this kind of system, you may have two kinds of events. There's a send event. S may issue a send event saying that it sent M. And R can issue a received event saying it received M. And a trace is a sequence of such messages. And a trace is authentic if in every trace, whenever you have a R receive M event in that trace, then in the same trace, there is a preceding event saying that S sent M. Okay? So these correspondence assertions, I think they are originally from some work by Wu and Lam in '93. Andy Gordon, who was here till yesterday, and Alan Jeffrey did a lot of work in this space too. There's a really nice paper by them in 2001 describing how you can prove these kinds of correspondence assertions by typing. So those are good references if you want to learn more about this. Then there's secrecy. And secrecy is that no information about any secrets that are exchanged between S and R leaks to the adversary. Intuitively, that's what you want. Now, the question is, how do you formalize this? And one way to formalize it is by an equivalence relation on traces. So essentially, what you want to say is that messages observed by A on the wire are independent of any secrets that may be exchanged between the participants, right? And in terms of language-based information flow, you may have seen this from Andrew Myers, I suppose, things like non-interference and so on. And one way to see it is that in terms of a programming language is that let's think of the sender as a function that takes some secret bytes and some public bytes and emits some bytes that need to be sent on the wire. And the sender satisfies this no leakage property if for any pair of secrets, S0 and S1, and a given public parameter, the sender, when applied to S0 and P, produces the same bytes as the sender applied to S1 and P. This is kind of like an ideal security property that you might want, that the result does not depend on the secret. Okay? You all buy that? Okay. Now, of course, this kind of ideal security is not attainable in practice. So, if the result computed by the sender does not depend on the secret, then the sender can't effectively communicate anything about the secret to the receiver. So, you need to do something. So, here's where cryptography comes in. And using crypto, you can kind of prove probabilistic security guarantees. You can say things like, the adversary cannot distinguish the bytes exchanged between S and R from a random string, except with a small probability. Okay, and the way these kinds of arguments are formalized are using cryptographic games. So a cryptographic game is a program that contains several procedures that have some shared state among those procedures. And the adversary is a program also that interacts with this game. And the objective of the adversary to win the game is to get the game to return some distinguished result. Say, get one of its procedures to return true. Okay? And the goal is to show that the probability of A winning that game is low. So, disclaimer, I'm not a cryptographer. Okay? Many of my colleagues are. And I'm kind of trying to interpret this kind of the modeling that cryptographers do in this through the lens of a programming language person. And if you want sort of the full story in some sense, I find this paper for what I'm going to cover in this lecture, this paper by Bellare and Namprempre in 2007 is actually a pretty accessible paper for a PL person, written by cryptographers. So you might want to check that out. The Wikipedia page is also surprisingly good, at least about ciphertext indistinguishability. So now we're going to look at a couple of games. And what I'm trying to build towards is to show you how we can model authenticated encryption in a system like F star. Authenticated encryption is a construction that lets you get both authenticity and secrecy out of some communication. Okay, and I'm going to start with how you model a game for secrecy. So do I have? All right, I think I can keep it big. So the first game is called NCPA, or indistinguishability under chosen plain text attacks. Okay, so the idea is that if you just parse the name of it, the attacker gets to choose a plain text and cannot distinguish between the ciphers that are produced for that plain text. Okay, so here's what the NCPA game looks like. Remember, a game is a collection of procedures that share some state. Okay, so the NCPA game is if you give me an encryption function that takes a key and a message, produces a cipher. Think of this as like AES or something. Okay, and an NCPA game on top of AES can be described by this piece of code. So what this code does is it first samples a random key, and then samples a random bit, and then it produces two functions. The first function is called left or right. The adversary can call left or right with two plain texts, M0 or M1. And the game, what it does is that based on the secret bit, it either encrypts M0 or M1 and gives the cipher back to the adversary. And then the adversary can guess the value of B, the secret bit. Okay, so it can, and there's a function here to check the guess. And if the adversary can get check to return true, then the adversary has won the game. Okay? Is that clear enough? Okay. The attacker's advantage, there's a notion of advantage here. The attacker's advantage is that it's their probability of guessing right more than half the time. Of course, they can win this game just by guessing randomly, right? Half the time. And this, you should take this as being a self-evidently correct formulation of ciphertext indistinguishability. This is a spec. Okay? So, right, that's my first point there. This is a spec. NCPA is meant to characterize the idea of ciphertext indistinguishability. Now, usually it's not possible to prove, given a particular encryption function, that say AES or something, it's not NCPA on its own. It's typically one makes a cryptographic hypothesis about some encryption primitive, claiming that it's NCPA with respect to some parameter epsilon. Occasionally, it is possible to prove sort of semantic security properties about individual encryption schemes based on hypotheses about the difficulty of certain problems. So, for instance, there's this encryption primitive called El-Gamal, and you can actually prove that it's semantically secure, but based on this assumption, decisional Diffie-Hellman. Diffie-Hellman is the decisional Diffie-Hellman assumption is based on the difficulty of computing discrete logs. So if it's difficult for an adversary to compute discrete logs, then any adversary that's able to break El-Gamal can also break decisional Diffie-Hellman. So in some cases, it's possible to get semantic security for sort of individual primitives, but not always. And in general, for what we do, this is kind of out of scope for us. We assume that a given encryption or hashing primitive or something has some semantic security property, and then we're going to build constructions on top of these primitives and show that the constructions are secure so long as the primitives are secure. Okay?
Sorry.
Yeah.
Exactly what does it mean for an encryption scheme to be NCPA? So that the attacker can only win some percentage of the time? Is that, or what does it exactly mean for? I understand what the procedure is, the game itself.
Yeah.
But what does it mean for an encryption scheme to validate that?
So, for instance, that an attacker that can distinguish El-Gamal encryptions with advantage epsilon can win decision Diffie-Hellman with probability epsilon over 2. Something like that. And it turns out for El-Gamal, the ciphertexts actually are they're random in some sense. They're distributed over the field in some sense. So it's possible to show for El-Gamal, and perhaps for some others too. But so NCPA was about secrecy. There's this other property called UFCMA, or unforgeability of chosen message attacks. That's a property that's suitable for use with message authentication codes, with MACs. So again, parsing the name a bit, the attacker chooses a message that they want to authenticate, and they aren't able to forge an authentic message. Okay? So the way this is set up is, a MAC, a message authentication code, is a keyed hash, typically. If you take a message and a secret key, and you compute a tag, a T out of it, such that it's really hard for an adversary to compute T unless they know the secret key, K. Okay? And the one way in which to formalize what it means for a MAC to be semantically secure is to do authentication by log lookup, in some sense. Rather than relying on the MAC alone, we're going to idealize the MAC using subshared state. So a UFCMA game looks like this. I have two functions, MAC and verify. And MAC takes a key, a message producing a tag. And verify is it's dual in some sense. It takes a key and a message and a tag and checks that the tag is in fact the MAC of the key in the message. Okay? And, oh, that X is spurious. Typo. Now, you should think of this MAC, for instance, as some algorithm out there, like HMAC SHA-1 is a MAC. There's many such MACs. Okay? And you can make an assumption about some MAC function by claiming by formulating that assumption as this game. And the game has a similar structure to before. We sample a random key, K. But now, instead of having a secret bit, we're going to actually allocate a log. And the log is going to be a bit of mutable state that contains a list of message tag pairs. Okay? And every time I MAC a message, I'm going to provide the adversary gets two functions, MAC and verify. And the MAC function, what it's going to say is that if you want to MAC a message, I'm going to compute its tag by using the raw MAC. But I'm also going to record the fact that M was MAC to T in my log. Okay, so I'm going to record all MACs that have happened so far. And then the verify function is going to call the raw verification of the MAC, get a result from it, and it's going to correct the result that this raw MAC provided by doing a log lookup. The raw MAC actually is not perfect. It's going to, with small probability, actually have collisions. So the ideal functionality is going to correct for those collisions by saying the raw hash needs to have checked out, but additionally, this thing is a valid, MT is a valid MAC only if this pair is also in my log. That's my ideal view of what a MAC is. Okay? So I see some puzzled faces as you, yeah?
So because it has to be in your log, that would mean like if the adversary stole the key somehow, it would not work, or?
So that's an interesting question. I think some of these models, they usually also account for things like dynamic compromise of keys. And what happens is, in that case, is that you may provide in addition to MAC and verify one more function called leak that says, if this thing leaks, I'm just going to release the secret key that's here. Leak is just going to be like a unit arrow key. And leak is just going to give the key to the adversary. But then what you're typically going to do is that every time you call leak, you're going to record the fact that you called leak in some ideal state, and then say that the verification, this verify function, the adversary can only win the game if you haven't leaked the key to them yet. So I'm showing you kind of the simplest model in some sense, but you can kind of enrich it by giving the attacker more power for different things. Other questions? So again, you should see this as a spec. There's nothing to prove about this. This is the spec of what it means for a MAC to be good. Okay? So the way I see it, a cryptographer, I write this piece of code in F star. A cryptographer should come and stare at this piece of code and convince themselves that this is in fact an accurate transcription of their understanding of UFCMA. Okay? So here's our goal. Our goal is that we want to build, like I said, an authenticated encryption that is given an NCPA encryption scheme and a UFCMA MAC. We want to build an authenticated encryption. And the way that it's going to work is that it's going to encrypt the plain text, MAC the ciphertext, and then concatenate the result. So the ciphertext of an authenticated encryption is a composite of a tag and a cipher, right? The dual of encryption is going to be decryption, and the way decryption is going to work is it's going to check the MAC first, and if the ciphertext is authentic, it's going to call decryption, and only then. And you can prove that this scheme is going to be semantically secure with an advantage that looks like the sum of the advantages of the two individual schemes. All right, so that's some background. Now, how do we actually model this stuff in F star? So first we start by actually writing an implementation of the primitive that we're interested in. So for hmax SHA-1, that's one Mac function. It turns out that it's it's basically a wrapper around SHA-1 that's kind of this is the message I want to Mac, and what it's going to do is it's going to somehow compute a SHA-1 of the key secret key concatenated or mixed with the message somehow. Okay, roughly that's what it's doing. There's not much to say about it except that it's just doing a bunch of operations on bytes and shuffling stuff around. Okay, but that's its spec. Now this is a pure function F star. If you try to run this, you can run it, but it's going to be kind of slow. So what we typically do is that this is our spec, and then we'll write an optimized implementation in C or assembly and prove that that implementation is a refinement of this one. Okay, so that's what hmax SHA-1 looks like. And now we want to assume that hmax SHA-1 is epsilon UFCMA secure. So how do we want to state that assumption? So ultimately, what we want to do is to state some kind of equivalence. Say, if you run hmax SHA-1, that's a program. This program is equivalent to the UFCMA version of hmax SHA-1 that's got this correction built around it. And there's many ways in which you can state such equivalences. The style we use in Everest is the following style, where we write both the concrete functionality and the ideal functionality together in a single program. So here's what it would look like. So this is the hmax SHA-1 game. This is the UFCMA game for hmax SHA-1. Okay, and it has the same structure as what I showed you before. You can sample a random key and you allocate a log. And there's two functions, mac and verify. And we're going to say that this function, there's kind of two control paths through it. There's the concrete control path, which is the actual raw version of hmax SHA-1, where these paths are toggled by these idealization flags that we have. Okay, so there's a Boolean called UFCMA that controls whether or not we want to apply the UFCMA assumption to hmax SHA-1. And here we say, if we're idealizing hmax SHA-1, then log the encryption. Otherwise, don't, and just do the normal hmax SHA-1 thing. And the verify is dual. It says if you're idealizing for UFCMA, then correct the verification. Otherwise, just return whatever the normal verification result is. So one way in which you should see this is that if you take this code and you specialize it while setting this flag to false, what you get is exactly hmax SHA-1. But if you set it to true, you get the ideal version of hmax SHA-1. Okay, so and code like this, every use of this branching in an ideal flag corresponds to a cryptographic hypothesis and needs to be audited by a cryptographer for, is this a valid spec in some sense? You always have to have someone stare at your specs. This is part of our spec. Okay? And what this spec is really saying is that this function mac verify, if you run it with UFCMA, this flag set to true, it is epsilon equivalent to mac verify with UFCMA set to false. Okay, so I was, as preparing this, I was expecting that presenting this to you would maybe that it wouldn't be completely obvious. I was expecting some questions. Yeah.
So, in my understanding, you're doing sort of product programs.
Yeah, exactly.
Taking non-interference rather than program equivalence.
That's right. Yeah, it's like building a product program, but in an interleaved fashion. Any other? Yeah.
Would you think of this or express it as a logical relation, since that?
Yep. You could, and in some cases we do, except in this style we find it more convenient to express it this way because we don't have a logical relation for all the features that we need to actually model these programs precisely. That includes private state. It's effectively would involve having a logical relation on C programs, and we don't have one of those. But that's an interesting direction. Like if someone, in a way, I would prefer if you could state this using a logical relation. I just don't know how. Yeah. Go ahead. Yeah.
You mentioned that there were like other approaches to making the same assertion.
Yeah.
And writing programs in parallel.
Yeah.
What are some of those?
I was thinking I might show you some of that tomorrow. But effectively, that would mean that's kind of like what Fritz is saying. Like you'd have there's a way in which you can for a fragment of programs where I know how to state logical relations, I can state these equivalences using logical relations. And I'll show you some of that tomorrow. But for this class of programs, we just build these product program constructions and express our assumptions that way.
Do you think that this format takes more advantage of users of 1-star?
In a way, we find that this style of doing things it's possible to scale to proving properties about 40,000 lines of C code. Right? Building a logical relation and sort of manipulating huge programs, side by side is, I hope we'll get there someday. But right now, I just don't know how to make that style scale. Other questions? Yeah.
So where is the epsilon?
It's a parameter. You assume there is an. We assume the equivalence. This is saying there exists an epsilon such that these two programs are equivalent. We don't manipulate the epsilon.
So you're assuming that that's just a proof written on paper somewhere that the cryptographer verified.
That's right. Or sometimes the cryptographer doesn't even have that proof. They just assume it. So that's kind of the whole game here. So you're doing reductions. If this thing is epsilon UFCMA secure, what can you conclude about something else? That's just a hypothesis. Sometimes there's no proof of the hypothesis. Now, the way this works then is that you do sequences of games. Like you build a composite construction using these primitives, and you transform them step by step. So if I build an authenticated encryption, some concrete authentication encryption that's doing encrypt and MAC, you can see that as an instance of the authenticated encryption game with the idealization flag set to false. If you unfold a bit, that's really the composition of the CPA game and the MAC verify game, both without idealization. And those are perfect equivalences. And then I can do one step of idealization and say, hey, I can idealize UFCMA, and I'm going to get a concrete version of encryption with ideal UFCMA. And then I'm going to transform this side, and I get ideal on both sides. And then this is perfectly equal to ideal AE, and so you can compose the whole thing and sum the probabilities over here. Okay, so that, in a sense, was kind of one half of the story. I described how we're going to sort of describe concrete and ideal versions of the program using this product construction, but I didn't say anything yet about how we do secrecy. And here's how we do secrecy. So secrecy in one guise in F stars, secrecy is expressed using parametricity. So let me ask you a question. So you have a function f at this signature, alpha or alpha. What is f of 0? 0, right? This is f star. It's total functions. Yeah. Right? That's parametricity, right? That alpha or alpha function is the identity function. What about this one? I have alpha or int. What's g of 0? Exactly. You don't know, but it's the same as g of 1, right? So the high-level idea is that well-typed code gains no information about its parametrically typed arguments, right? And that's relational parametricity from Reynolds and and then Wadler, and then lots of work on this stuff. So I expect some of you are familiar with this line of reasoning. So the same idea with parametric polymorphism also applies to abstract types. So if I have a module that provides a type of plain text, an abstract type of plain text, plain, and I have a client function of type plain arrow int, what's client.f applied to P? Same deal, I don't know, but it's the same as client of f applied to Q, right? And actually some recent work by Carl Crary shows that how to lift this kind of thing to the level of modules. It's again I think we appeal to this kind of reasoning all the time, just even informally as we write typed programs. So this is what we're going to do to model secrecy. We're going to model up plain text using an abstract type of plain text, and our abstraction is going to be a little fancier than having just a fully abstract type like val plain. We're actually going to give you an interface to work with plain text, but it's going to be a little subtle. So a plain text concretely is just the bytes of a plain text. And I'm going to give you two functions to coerce between plain text and bytes, but at a restricted interface. So if I have a plain text, I can view a plain text as bytes. That's breaking secrecy. But you can only do that if you're not playing the NCPA game. NCPA is trying to enforce ciphertext indistinguishability to protect the plain text. The ciphertext is a function of the plain text. So the plain text is the thing that's being kept secure. So the plain text is going to be kept secure so long as you're not doing NCPA. Okay? And dually, I can go from raw bytes to plain text, breaking the integrity of plain text. And I can do this only if I'm not idealizing the UFCMA game, because that one is about authenticity. Okay? So I'm going to represent my plain text using this type. And now I can do NCPA at f star. Okay? So here's how NCPA works. It's roughly similar to the pseudocode I showed you earlier. But here, NCPA says I'm going to sample a random key, and I'm going to allocate a ideal log. And I'm going to show you why I need that log in a second. And here's what I'm going to do. If I'm going to encrypt the plain text, P, I need to produce a ciphertext, which is bytes. And what I'm going to do is that when I have to encrypt these bytes, if I'm idealizing the NCPA game, instead of idealizing bytes, instead of encrypting the bytes that the adversary asked me to encrypt, I'm going to just encrypt zeros instead. Okay? And otherwise I'm going to encrypt the actual bytes. And when I encrypt zeros, that's when I'm idealizing, I'm going to log the fact that this plain text was encrypted to that cipher. Okay? So this is, in a way, this is doing encryption as table lookup. I'm just going to disregard the plain text, encrypt zeros instead, and then correct for this idealization using a table. Okay? So and now the thing is, this function is well typed against that interface for plain text. And so by parametricity, this function does not leak any information about the plain text when NCPA is true. Okay? So again, this is spec, right? Like you have to trust that this is an accurate characterization of NCPA. So if you're skeptical about it, you ask questions. This is supposed to be evidently an NCPA. Okay? Now, NCPA is actually interesting because NCPA is only one half of the encryption game. The adversary only gets encrypt. The adversary does not have decrypt in the NCPA game. But in order to actually implement a functionally correct encryption, I need a decryption half of it too. And so the decryption half of NCPA is very much, it has to correct for the idealization of that I did on the encryption side. So essentially, decryption is going to if I'm idealizing, it's going to search in the log to do decryption instead. Okay? Now, this is these kinds of constructions. Authenticated encryption gives you authenticated encryption for a single message. If you want to do a protocol like TLS, you need to generalize this to streams of messages. And if you look at what an ideal functionality for streams of encrypted data to look like, the way it works is that, let's say I have this is the sender, that's the receiver. The sender wants to send a message like, say, attack at dawn. And this is going to get fragmented into two messages, attack at and dawn. This is going to be encrypted down to two ciphertexts. But concretely, this is just going to be ciphertext. But ideally, what's going to happen is that we're going to log these ciphertexts with the corresponding plaintext in an ideal encryption log. Send these messages over to the adversary, and the adversary is going to decrypt. Concretely, they're just going to decrypt the cipher, but ideally, they're going to do table lookup. And that's our spec, in some sense, of streaming authenticated encryption. And we're going to prove that you can get this kind of spec, this for streaming authenticated encryption, based on just NCPA and UFCMA about the primitives. Okay, so that's kind of the whole verification effort is how do you provide this self-evidently, view of ideal streaming encryption using raw primitives. Now, to do such a proof, so we did a proof of this for the TLS record layer. That's kind of too small, but it's just to say that these proofs take a lot of work. So this is a proof of the TLS 1.3 record layer, and this proof does the streaming authenticated encryption thing, and it roughly takes about 15,000 lines of F-star code for producing about 8,800 lines of C code. And the end result is this streaming property. Okay, so now I'm going to switch into kind of demo mode and show you some F-star code and how this really works. You see, you need it bigger, right? Questions before diving into? Is that big enough? Ish? Okay. I can make it bigger still here, I think. Okay. So this is F-star in Emacs. And the way it works is kind of like proof general or something. Like you can step through F-star code just by getting it to type check chunks of it at a time. And you can kind of see the difference in color. The type check part is kind of a light blue. The suffix of the buffer is still to be checked. So what I'm showing you here is an interface for authenticated encryption. So this is the spec I want to provide as authenticated encryption. And I want to convince you that this is a good spec in some sense. So authenticated, yeah?
That bar, is that a comment? Or?
The bar is a comment. Yeah, it's triple slash gives you this kind of a red bar in the margin. Yeah, do ask, like, there may be lots of like syntactic questions, and so please ask if you don't see something. So this is saying authenticated encryption provides you with an abstract type of keys, and these keys have some type. This is saying that the type happens to be in universe 0. Okay. There's a authenticated encryption cipher, and it's also an abstract type. It supports equality in this example. And then we have we're going to do all this with. So in the code I was showing you in my slides, I was hiding some detail about how you have to manage specifications that involve state. And typically, when you're writing stateful programs, you have to reason about the footprint of the program, what memory it's going to read and write. So these footprints play a role here. So there's an abstract footprint associated with a key that's going to be kind of the reference that holds the key's ideal log. Okay, that's the way you should think about it. And one way to look at this function is that it's a function from keys. This G tot here is F star notation for saying it's a ghost total function, meaning that it has no computational relevance. It will be erased at extraction time. Okay? And it returns a loc. A loc is a type from our library that says this is an abstract location, memory location. Okay? Keys have an abstract invariant that says a key and a particular memory, hs.mem, that's our memory model for heaps. And in a key is well formed in a particular memory. That's how you should read the shape of this invariant. And authenticated encryption is going to be based on logs. The way we're going to specify it is that there is an authenticated encryption log, AE log, that given a key and a particular memory, given that the key satisfies its invariant, you can read from the key a log of entries, a sequence of log entries, and each log entry is a pair of a plain text and a ciphertext. Okay? And now there's three main functions in the interface. There's key generation. So that says you can always call key generation, that its precondition is true. It's a stateful function that returns a key. And its postcondition is a relation between the initial state, H0, the key it returned, and the final state, H1. That's like a Hoare-style spec for keygen. The spec says it modifies no existing location in the heap. That modifies loc none, saying the initial heap and the final heap, all existing locations in H1 H0 did not change in H1. It provides a key that satisfies the invariant. And it says that if we're idealizing authenticated encryption, then after key generation, the encryption log is initially empty. Okay? Now we have two functions, encrypt and decrypt. Encrypt takes a key as a key and a plain text and returns a ciphertext. It requires the key invariant to be called, and it ensures afterwards that the key invariant is still true. It modifies only the key. It may modify the key's log, for instance. And what it says is that if we're idealizing authenticated encryption, then the encryption log at the end is the concatenation of the encryption log at the beginning with one new entry. SNOC is cons backwards, right? So it's adding an element to the end. And decryption is the converse. It says, hey, if I have a key and a ciphertext, I'm going to try to decrypt it and return to you a plain text, maybe an optional plain text. Again, I require the key invariant. I'm going to ensure the key invariant again. I didn't change anything in the state. But if I'm idealizing and I successfully return to you something, some question mark is that the result, which is an option, is actually in the sum case. Then the authenticated encryption log actually has this entry in it. The plain text, sum question mark .v, projects the value stored in the sum and the cipher. Okay, I just threw a bunch of code at you. So, what did you make of it? Does it capture your intuition of what authenticated encryption should be? Bits of concrete syntax that you didn't understand? Yep.
Why exactly are you using a SNOC list?
I could use a cons list if I wanted. I'm just, I'm no particular reason. I'm just adding things. The sequence in the list, I see them as sort of the new stuff goes at the end. No particular reason. Yeah. It's spec anyway, so it's not like it's computationally. It doesn't make a difference one way or another. That's just spec, so it doesn't. Other questions? Okay, so now I have to provide this. This is just an interface. I have to actually implement this interface. And when I have an implementation of it, I'm going to show you bits of it. And when you have a development like this, a mechanically checked proof, oh, that's way too small. what one usually does is to grep through the development to see what assumes there are, right? And in this case, what you should grep through is, in addition to searching for assumes, you should search for all uses of idealization. Each one of them represents a spec too. So how am I going to make this big enough for you to see that? So let me assure you that in this code base, in this development, there are two kinds of assumptions. So there's one assumption here, which this code is online, by the way. If anyone's interested in playing with it, you can. The first assumption is an actual assume, and it's an exercise that I left you guys, okay? The other kinds of assumes are actually, every use of idealization is guarded by a use of one of these functions, flag.idealizing. So every time I branch on an ideal flag, the F-star type system will force me to guard that branch with one of these function calls, flag.idealizing. And I need to go look at flag.idealizing to check that that it reflects my hypothesis about a game precisely. So here is the encryption game for NCPA. We've seen it a couple of times now, so hopefully this time it's in actual code, it's maybe a bit more approachable. So this is the NCPA game. This is in a file called OPLSS.cpa. And the encryption game for CPA is saying here, it has a key, it has a plain text, it's going to produce a ciphertext, and its body is going to say, well, it's actually a little bit more interesting than what I've shown you before, because if you want to do AES encryption, which is what this is doing, you also need to use initialization vectors. And that's the level of precision that you have to get. I mean, to actually get an implementation, you need to go down to this level of detail, and then some, like constrain the lengths of the text, ciphertext, and the plain text, and so on, as determined by the algorithms. So here's the definition of ideal AES as an NCPA game. You need, given a key and a plain text, you need to generate a fresh initialization vector. That's like incrementing a counter. And then if I'm idealizing NCPA, I'm going to this is zeros. I'm going to set the plain text to a sequence of zeros. Otherwise, I'm going to use the actual plain text. And here I'm going to break confidentiality of the plain text by using plain.repr, that function I showed you before. But I'm not idealizing NCPA, so it's fine. I can do it. And then I call actual AES. I get a ciphertext. The representation of an AES ciphertext is actually the concatenation of the initialization vector and the ciphertext. I then, if I'm actually doing NCPA, I need to correct for this idealization by logging in a log this entry that maps the message to the ciphertext. Okay, and so that's NCPA for AES. One half of it. And the decrypt side is, again, similar to what I've shown you before. Like if I want to decrypt a key and a ciphertext, I'm going to look at the key. The key contains the raw key and an ideal log. And I have to call raw AES decryption on the cipher part, passing in the IV and the ciphertext. And then if I'm idealizing, I'm going to correct for this decryption by doing a log lookup. Otherwise, I'm just going to return the log, return the plain text. Okay. And so let's look at the implementation of authenticated encryption. I have 3 minutes more, right? Yes. So an authenticated encryption key is just a pair of a MAC key and encryption key, and it comes with an invariant that says, well, these keys, they have some ideal logs associated with them, and I need to say that those logs are actually disjoint in memory. Okay, so think of it in terms of something like separation logic or something. You need to actually say that these don't alias each other, and that an authenticated encryption cipher is a pair of an IV of an AES cipher and an HVAC shop tag. That's because it's encrypted, right? And then in order to provide this invariant, I'm actually, notice that in order to actually implement authenticated encryption, I'm not going to use any further idealizations. I'm searching for idealizing in this buffer. Okay, I'm not using flag.idealizing anywhere here. Okay, so I'm making no further crypto hypotheses when implementing authenticated encryption. I'm just using the ones that I've made on the primitives. But I still have to implement this AE log. The AE log is a map. I showed you that before, right? So an AE log is a map between plain text and AE ciphers. And there is no existing log that contains that. The CPA log maps AES ciphers to plain text. The MAC log associates tags with plain text. I now need some composite log that's going to sort of interleave the two somehow. And that's my AE log. So I need to materialize this AE log out of my existing logs somehow. So I can do that by saying the AE, this is the key that makes this proof work. There's an invariant here that relates the two logs. It says the invariant of the authenticated encryption construction, and that's an AE key in a particular state. I need the invariance of its components. I need the CPA invariant on the encryption key, the MAC invariant on the MAC key, and I need one more piece which says that if I'm idealizing MACs, then the only entries in the MAC log are actually CPA ciphers. I'm not going to MAC anything else. The only things that are authentic are ciphers produced by CPA. Okay, and that relation among the MAC log and the CPA log is what's going to let me build this composite log. And it turns out that for this proof to go, you need other invariants on the CPA log. For instance, you need to know that every ciphertext is unique. And you wouldn't be able to get that if you didn't have IVs. So that's where the verification effort comes in. You need to sort of, from the basic functionalities, impose other invariants upon it so that you can present this authenticated encryption view upon things. So at the end of the day, given that you set up those invariants, and you have to do a bunch of proofs about it to say that, for instance, if I have this property that's related, that MACs are, only the CPA ciphers are MAC'd, then I can conclude that some property about the composite logs. And you have to write proofs about that stuff. And once you do, you can, here's the composite construction, which is, at the end, turns out to be really simple. So to generate an AE key, I generate a CPA key and a MAC key. That's it. To encrypt, I do a CPA encryption, and then I MAC the ciphertext, returning the pair. And to decrypt, I'm going to do a MAC I'm going to decompose the ciphertext into a ciphertext and a tag. I'm going to verify the tag, and then I left this in here. I could have polished a little bit to remove these two lines, but I left it in here for a reason. So concretely, what you want to do is to just say, I'm going to do a verification followed by a CPA decryption. But I have these two additional lines in here, and these two lines are actually just proof steps. So here, I'm calling a function. This function actually is just a lemma. It's a unit returning pure function, meaning it has no computational relevance. All it's doing is showing that from the invariants from the postconditions of the functions that I've called so far, I can conclude the precondition I need to call CPA.decrypt. And I can branch on a flag, and this branch is a form of a branch that ensures that the branch is computationally irrelevant. So these kinds of branches are safe. They don't represent crypto hypotheses. So anyway, so that's my demo. Happy to have questions. Otherwise, more tomorrow.